Welcome to qnawire.
So we have two independent exponential random variables with parameters lambda1 and lambda2. That means the PDF of x is lambda1 e power minus lambda1 x, where x positive and 0 else. This is the PDF of the random variable x. And the PDF of the random variable y will have a parameter lambda2 e power minus lambda2 x. Y positive, 0 else. So these are the two independent exponential random variables that is given. So now the question is, what is the probability that x is greater than y? Since these two are independent, the joint PDF will be the product of the individual PDF. So the joint PDF of the random variables x and y is the product of the marginal density functions. So that means the the joint PDF of the two random variables is given by lambda1 lambda2 e power minus of lambda1 x plus lambda2 y when x and y are positive and 0 otherwise. This is the joint PDF. Now the probability that x is greater than y, this is what we need to find. That is basically the probability that x is greater than y is basically, this is a subset. So what is this region? This region is x positive, y positive. So let's pictorially draw x positive, y positive. X positive, y positive is basically the quadrant 1, first quadrant, Q1, first quadrant. That means this entire space, this complete space. Now x is greater than y. X is greater than y is, let's draw a straight line. X is equal to y. So this is x axis, this is y axis, this is x is equal to y. X is greater than y is this region, this complete region. So now this is the region we need to integrate over. So what we do is we'll choose a typical x. The typical x is going from 0 to infinity, but the typical y goes from 0 to x because the exit of y is at x and the entry of y is at 0. So that means probability that x is greater than y is x going from 0 to infinity, y going from 0 to x, the joint PDF, and dy dx. This is the order of integration we need to do. So that means let's perform the integration now. So it is integration of x is 0 to infinity, y is going from 0 to x, joint PDF, which is lambda1, lambda2, they are anyway constants, I'll keep it outside, e power minus lambda1 x, e power minus lambda2 y, dy dx. First we need to do integration with respect to y. So x is 0 to infinity. This you can drag it out because that doesn't have any y. So e power minus lambda1 x. Now what is the integration of e power minus lambda2 y? It is e power minus lambda2 y divided by negative lambda2. Now substitute the upper and lower limits. Y is 0 and y is x. And then we need to do integration with respect to x. So this lambda2 gets cancelled, so minus sign you bring it out. So minus lambda1 integration x is 0 to infinity e power minus lambda1 x into, when you substitute upper limit it is e power minus lambda2 x minus when you substitute lower limit e power 0 which is 1 dx. So that means it is negative lambda1 into x is going from 0 to infinity e power minus of lambda1 plus lambda2 x minus e power minus lambda1 x dx. So now let's perform the integration with respect to x. So it is minus lambda1 into, this is e power minus of lambda1 plus lambda2 of x divided by minus of lambda1 plus lambda2 minus, and this one is e power minus lambda1 x divided by minus lambda1. Now substitute 0 and infinity. For infinity, anyway, both the exponentials will be 0 because e power negative infinity is 0. Remember, the parameters lambda1 and lambda2 are positive. And when you substitute the lower limit, so I'll get minus sign of, so minus of e power 0 divided by minus of lambda1 plus lambda2 plus 1 by lambda1. So basically it is lambda1 into 1 by lambda1 minus 1 by lambda1 plus lambda2. So taking LCM, you will get lambda1 lambda2 divided by lambda 1 into lambda 1 plus lambda 2. Lambda 1 cancel, so the answer is lambda 2 by lambda 1 plus lambda 2. So this is the final answer for the probability that x is greater than y. Now we have another random variable z is equal to min of x comma y. We need to find the probability distribution of this min of x comma y. So let's start with the CDF of the random variable. Fz of z is probability that z is less than or equal to z. That means the probability that min of x comma y is less than or equal to z, which I can write it as 1 minus probability that min of x comma y is greater than z. When minimum of x comma y is greater than z, suppose if you draw a number line, suppose x is minimum and y is maximum. If the minimum is greater than z, that means x is greater than z, then the number greater than the minimum, which is y, is also greater than z. So that means I can write this as probability that x is greater than z comma y is greater than z, which I can write it as 1 minus, since the random variables are independent, it is probability that x is greater than z whole square, because both are identically distributed, which I can write it as 1 minus probability that x is less than or equal to z the whole square. So this is the cumulative distribution function of the random variable z. That is nothing but 1 minus fx of z the whole square, where fx of z is the cumulative distribution function of x. What is the cumulative distribution function of the random variable x? Fx of z is what? Or we can take it as fx of x as of now. Fx of x. It is 0 when x is less than 0, less than or equal to 0. It is 1 minus e power minus lambda 1 x when x is positive. This is the CDF of random variable x. But we got the CDF of random variable z as this. So let's take cases. When z is less than or equal to 0, what is fz of z? When z is less than or equal to 0, what is fx of z? It is 0. So substitute 0 in place of fx of z. It is 1 minus 0 whole square, which is 0. So it is 0 when z is less than or equal to 0. Now when z is positive, we will get fz of z as 1 minus of 1 minus e power minus lambda 1 z the square. So basically it is 1 minus e power minus 2 lambda 1 z. This is the since the random variables are independent, I can write this as 1 minus probability that x is greater than z into probability that y is greater than z, which I can write it as 1 minus probability that x is less than or equal to z into 1 minus probability that y is less than or equal to z, which is nothing but 1 minus fx of z, which is CDF of random variable x, into 1 minus fy of z, which is CDF of random variable z. This is my CDF of random variable capital Z. So 1 minus CDF of x into 1 minus CDF of y. What is CDF of exponential random variable? For x, it is 0 when z is less than or equal to 0, 1 minus e power negative lambda 1 z when z positive. And similarly for random variable y with parameter lambda 2, it is 0 when z is less than or equal to 0 and 1 minus e power minus lambda 2 z when z is positive. In both the cases when z is less than or equal to 0, the CDF is 0. So that means fz of z is 1 minus 0 into 1 minus 0, which is 0 when z is less than or equal to 0. And finally, when z is positive, my CDF of z is 1 minus of 1 minus e power minus lambda 1 z into 1 minus of 1 minus e power minus lambda 2 z. So basically that will be 1 minus e power minus of lambda 1 plus lambda 2 z. This is when z positive. So finally the CDF of the random variable z, which is defined as min of x comma y, is given as 0 when z is less than or equal to 0. It is 1 minus e power minus of lambda 1 plus lambda 2 into z when z is greater than 0. So now when you differentiate, you'll get the PDF. The PDF of the random variable z is e power, lambda 1 plus lambda 2 times e power minus of lambda 1 plus lambda 2 z when z is positive, 0 otherwise. So if you can see, this is also an exponential random variable with parameter lambda 1 plus lambda 2. That is what the question is asking. And so the mean of this random variable, that is expectation of z, is 1 by the parameter, that is lambda 1 plus lambda 2. And the conditional distribution of z when z equal to x is x itself. Because when z equal to x, the random variable z will be x itself. Because it's given that z equal to x. So the conditional distribution of z equal to x given z equal to x is fx of x itself.